Yeah. Day 3, summation formulas. Yesterday we looked at how we can use rectangles to estimate the area under a curve. We can draw rectangles from the left side to get the left sums, or the right side to get the right sums. That also produces upper and lower sums that are above or below the actual value. And then we kind of briefly discussed how we can use more and more rectangles to get a more accurate estimate. Well, the optimal number of rectangles to use is to use an infinite amount. So we want to approach an infinite amount of rectangles. And that's where we get the area of a region in a plane. We're going to take our height of our rectangles, which we got right here, f of c sub I, c sub I just being whichever leg of the rectangle you're at, times delta x, where delta x is b minus a over n, where a and b are the left sides of the region. And then we want to add up all these rectangles, n rectangles, where n approaches infinity. I would pause the video if I were you and kind of write this formula down so you can kind of use it as we go along. As we work through these rectangles, these summations, we want to use the summation formulas. You can't use your calculator to sum up an infinite amount of rectangles. You need to have your formulas and use the limit definitions of a limit at infinity. So if you don't have these formulas written down, I'd pause and write these down too. Our first area we want to find is the area under the cubic, f of x equals x cubed, from 0 to 1. So basically this region right here. Now they kind of drew a rectangle here. So we're going to find the area underneath this curve. Right? So we want to use our rectangles, starting with 1 and going to n rectangles. We want to find our function times the width. And we want to do it an infinite amount of times. Now, if you look back, delta x is b minus a over n, where b and a are the endpoints, so 1 minus 0 over n. And n is going to approach infinity. So that part's going to be 1 over n. Now, our function, we want to evaluate it. And we want to have our infinite rectangles. Each rectangle is going to be so high. And we want to evaluate it at either the left or the right. If we evaluate it at the right, it'll be I over n. Because as I equals 1, it'll be 1 over n, and then 2 over n, and then 3 over n, until you get to n over n, which is 1. So we're going to stick I over n into our function here. So we're going to have the limit as n approaches infinity from I equals 1 to n of I over n cubed times 1 over n. And then it's simply a matter of pulling out our constants and using our summation formulas. I can pull out n cubed, 1 over n cubed, and then n. So we'll have the limit as n approaches infinity of 1 over n to the 4th. This is n cubed and this is n. As we sum from 1 to n of I cubed. You look back at your summation formulas, the I cubed formula is n squared times n plus 1 squared over 4. I'm going to distribute the squared. So I'll have n squared times n squared plus 2n plus 1 over 4. All right, we'll continue. We'll distribute the n squared. We got n to the fourth plus 2n cubed plus n squared all over 4n to the fourth. The limit of that as n approaches infinity. Now, if you remember your rules for limits at infinity, when the degree of the top and the bottom are the same, you divide the coefficients. So the area under this curve is 1/4. And if you kind of draw it out and kind of think about it a little bit, that area, 1 times 1 is 1. If you cut it in half, it would be half. And you can see it's roughly half of the half, which is 1/4. It's actually exactly half of the half. All right, now I know that that is a mouthful, and it's a lot of algebraic manipulation. The main idea you need to get from this is that you're taking all of these rectangles and adding them up, right? You're accumulating rectangles as you move from the left to the right. It's an accumulation process. All right, let's look at another example. All right, we're going to find the area under y equals x squared plus 1 from 0 to 3. All right, let's draw it out and sketch a few rectangles. Okay, x squared plus 1 from 0 to 3. And we're going to have a few rectangles. All right, so our area will be adding up rectangles from 1 to n of our function, which will give us the height, times the width, which is delta x. And then we want to approach an infinite amount of rectangles. So as we start this, from the left side, our rectangles will be evaluated at this time it's 3i divided by n. Because the gap is no longer 1, the gap is 3. So when we stick in I as 1, we'll evaluate it at 3 over n, and then 3 times 2 over n, and 3 times 3 over n, all the way up till we get to 3 times n over n, which will get us to 3. So we'll evaluate our function at 3i over n squared plus 1 times, and then delta x is b minus a over n. This is b, this is a, so 3 minus 0 over n. All right, we can pull this out right away. So we got 3 over n, because our variable is I, we can pull out that. And then we want to sum up. If we square this, we get 9i squared over n squared plus 1. Okay, and as we continue, the summation for I squared, the 9 over n squared is going to stay. The summation for I squared is n times n plus 1 times 2n plus 1. Should have that formula down. I'm going to distribute a little bit, so we'll have n squared plus n times 2n plus 1 over 6. And then the summation for 1 is just 1 times n. All right. As we continue, again, this is going to be a lot. The thing to remember is it's this accumulation of rectangles. You can remember that, you should be all right. I'll distribute up top. This is a FOIL. So we still have 3 over n, 9 over n squared. FOIL up top, we got 2n cubed That's first. Outside would be n squared. Inside would be 2n squared plus n over 6 plus n. All right, let's distribute this first 9 over n squared. We'll distribute the 9 over n squared. We'll get 18n cubed plus 9 times n squared. 9 times 2n squared, that'd be 3n squared, so 27n squared. Plus 9n over 6n squared plus n. All right, let's distribute our 3 over n. That can cancel and just distribute 1 over n to the 2. So we got, as we distribute this, we got 18n cubed plus 27n squared plus 9n over 2n cubed plus this time we can't cancel the 3, so this would be 3n over n because there's no 6 to cancel it with, so we just leave it. And then again, remember your rules for simplifying here. The degrees are the same, so divide the coefficients. So it'll be 18 over 2 is 9. Here the coefficients are the same, so divide the coefficients. 9 plus 3 is 12. So the area under that curve is 12. So you can see accumulating all the rectangles, infinite amount of rectangles, we get the area under the curve, which is 12. And you can kind of estimate it. This is 3. 3 squared plus 1 is 10. So this is 30. It's a little bit around half of 30, which is around 15. So 12 is a pretty good value. 15 is a good estimate, 12 is the value. So in conclusion, in review, to find the area under a function, use rectangles. The more rectangles, the better. In fact, the infinite rectangles, the best. Take your rectangles, approach infinity with your rectangles.